have Ellen Zweibel speaking to us today about cosmic rays. So Ellen is an expert in fluid dynamics and plasma physics. She's worked on a really wide range of topics, everything from stellar interiors to the interstellar medium to things like clusters of galaxies. So she really has quite a breadth to her research, as is evidenced by her. I know she's spending a lot of time on the decadal survey right now. And I also learned that she got some of her scientific start in Boulder at the High Altitude Observatory, which is where I did my first REU. So it's a small world for astrophysicists. And thank you, Ellen, for coming to talk to us today. Go ahead and take it away.
Thank you for the invitation, Jim. Can everybody hear me? I assume that means yes. Okay, yeah. So I'm going to talk about cosmic rays and multiphase gas. Before I do that, I'd like to acknowledge this subset of my collaborators whose work is especially relevant to what I'll talk about today, especially the work of Chad Bustard, who's just started as a postdoc at the KITP. So, oh, how do I, this is not good. I'm trying to advance my slides and I'm sharing my desktop. Here we go. Okay, so to kind of set the stage, I'd like to begin by talking about star formation feedback. So probably we all know what star formation feedback is. Star formation is self-limiting due to radiation pressure and radiative heating, to the production of hot gas, and to the production of cosmic ray particles, which, as we'll see, comprise a fairly small fraction of the energy output of stars, but it turns out to be a very important fraction. And here I've just shown some interstellar bubbles seen in the infrared, sculpted by winds and luminosity from massive stars, and here the endpoint of stellar evolution, supernova remnants. So not only do stars regulate the rate at which they form, but their energy output sculpts the interstellar medium and can drive galactic winds. And galactic winds are multiphase. Here are two views of the wind of M82, which is sort of the obligatory poster child for galactic winds. Here on the right is a composite image. So X-ray emitting hot gas is shown in blue, red, H alpha. Here's the optical disk of the galaxy. This is sometimes called a super wind. And you can see from this far infrared image, in actually a polarimetric image, how the magnetic field of the disk is being dragged out by this wind. So cool gas at some level also seems to be participating in the wind of M82. Now, these different components of galactic winds are not necessarily all driven by the same thing, but it's still interesting to ask what the possible drivers are. So the most obvious one is thermal pressure from gas that's been heated in the disk. And somewhat surprisingly, these models generally fail because the gas cools. Cools due to radiation, it cools due to adiabatic expansion. Radiation pressure is probably effective in some cases, but now that we have high resolution three-dimensional simulations of radiation pressure driven winds, it's observed that the radiation tends to sort of squirt out through low density holes and doesn't take a lot of gas with it, almost by definition. And then there's cosmic ray pressure. And cosmic rays cool more slowly than thermal gas. And they're magnetically coupled to all the gas in the galaxy at some level, which maybe raises the hope that they don't just leave through low density channels, but the physics, as we'll see, is a lot more complex. And here, kind of in a nutshell, is an argument for why a gamma equals 4/3 gas is more effective at driving a wind than a gamma equals 5/3 gas. So this is just a pressure-driven wind. There's a trade-off between the high sound speed material at the center, which gradually transfers its energy, and we wind up with these asymptotic velocities. So to investigate cosmic ray driving of galactic winds further, and the whole question of cosmic ray feedback, we have to understand how cosmic rays actually exert pressure on thermal gas. So with this as motivation, here's the plan of my talk. I'll go through a few salient properties of cosmic rays, why we describe them the way we do. Then I'll talk about a theory of how cosmic rays regulate their own confinement in the galaxy by something called the streaming instability, and how the streaming instability naturally leads to something called a bottleneck, and what the consequences of bottlenecks are. And then I'll kind of break new ground and talk about another instability, which is driven by an anisotropic pressure tensor of the cosmic rays. And I'm going to propose that this actually complements the streaming instability as a confinement mechanism. And then I'll discuss some conclusions. And I understand that the culture here is to ask questions. So please, do feel free to interrupt and ask questions. I'm going to go through a lot of things a little bit fast, and I expect to be challenged, and that is all good. So we're probably all familiar with the collisional processes associated with cosmic rays. The low energy cosmic rays are an important source of heating and ionization in interstellar gas. They also drive interstellar chemistry. This opens the door to a lot of diagnostics of cosmic rays, which I'm not really going to discuss, but I think they have a potential which is, still not completely tapped. What I'm going to focus on are the collisionless processes, which lead to the pressure support, can drive a large-scale buoyancy instability, thermal instability, galactic winds, and a source of heating. And these collisionless processes are all fundamentally based on kinetic scale mechanisms that are mediated by the ambient magnetic field, the interstellar magnetic field, the intercluster magnetic field, whatever the background field is. And we're going to be looking for, since we can't do kinetic scales on kiloparsec or certainly megaparsec scales, we're going to be trying to develop a fluid description that's relatively robust and that adapts to not only the local, but the global conditions, and how it can be tested and how it can be implemented in numerical simulations. So that is the program. Okay, so what about cosmic rays? Well, I like this image of the cosmic ray energy spectrum, in part because it shows you the vast array of experiments that have gone into characterizing the spectrum. This also shows the flux of cosmic rays at the Earth. You can see that it extends from actually less than a GeV to 10 to the 12 GeV. It's normally characterized as a broken power law. It's mostly protons. Electrons are 1 to 2%, positrons even less. The energy density in cosmic rays in the Milky Way is about 1 eV per cubic centimeter, which is similar to the magnetic, thermal, and radiation energy densities. Is there some profound significance to this? I'll address that, I think, on the next slide. The number density of cosmic rays is very tiny compared to the mean density of interstellar gas, which is about 1 per cubic centimeter. And the mean energy of a cosmic ray is a few giga electron volts. So is equipartition universal? No, it's really not. This is some work by my former PhD student, Tove Joost Hull. And basically what you can see here is that for the Milky Way and M31 and the Large Magellanic Cloud, there actually is a good equipartition between magnetic fields and cosmic rays, and also magnetic fields, radiation, and so on. But as we go to more extreme systems, first to starburst galaxies M82 and NGC 253, the cosmic ray energy density doesn't quite keep up. And in an even more extreme system like ARP 220, which is probably the closest ULERG to us, the cosmic rays are really way down. And this is because losses in these environments are very strong, primarily collisional losses. And so you never build up an energy density in cosmic rays that compares to the magnetic or radiation energy density. So what about the composition of cosmic rays? Well, here it is compared to solar system abundances. And it's actually not that different from the solar system, with the notable exception of this enrichment of light elements, lithium, beryllium, and boron. And their abundance is usually interpreted as being due to spallation of carbon, nitrogen, and oxygen cosmic rays on interstellar material. So from the abundances of these elements, we can deduce that cosmic rays have passed through something like 3 to 5 grams per square centimeter from source to detection, which, if they were confined to the galactic disk, would imply a lifetime of a couple of million years. But from radioactive isotope ratios, we actually infer a longer confinement time in a medium with a lower mean density that suggests that cosmic rays sort of move between the disk and the halo. There's a notable lack of elements that are R-process elements formed in supernovae, and that's led to the conclusion that cosmic rays are accelerated from the interstellar medium, most likely by supernova energy, but they're not by themselves supernova ejecta. They're very isotropic. It's hard to measure the directional anisotropy below about a TeV because of strong modulation within the heliosphere. But where we can measure it, we see that at a TeV, cosmic rays are isotropic to about 1/10 or 0.2%. The anisotropy does increase with increasing energy. Here, they're probably extragalactic in origin, no reason to expect them to be isotropic, but we can explain the anisotropy, small anisotropy, as well as the long confinement time by postulating that cosmic rays have a mean-free path for scattering, which is of order a parsec, and that increases with energy. So that parsec value is representative of the sort of mean cosmic ray energy. Okay, so that was a whirlwind introduction to cosmic rays. They're accelerated from the interstellar medium in pretty much one-shot events that produce an e⁻² spectrum, but it's steepened by energy-dependent losses, primarily here, escape. They're confined to the Milky Way for about 20 million years. They're scattered with a mean-free path of about a parsec, and about 10%, this should say power, not paper, will maintain cosmic rays in a steady state. And they're observed in star-forming galaxies with a wide range of properties, going from dwarfs to ULERGs and AGN. So a schematic for the propagation might look something like this. So galactic magnetic fields have a mean component, but they also wander. They kind of leave the disk and come back to the disk. And cosmic rays tend to stay pretty much on their own field line or small bundle of field lines. But along those field lines, they scatter back and forth. So it's kind of a compound model. They wander through the galaxy on wandering magnetic field lines, and they scatter up and down the field lines. And we can translate what we know about the mean-free path and the confinement time to a sort of effective diffusion coefficient of about 3 × 10⁻28 centimeters squared per second. So if you can remember that number, that would be convenient. Okay, so how do cosmic rays actually interact collisionlessly with the background medium? Well, the perpendicular dynamics are actually easy, although it looks kind of like a sleight of hand. The cosmic rays have no inertia, so they're kind of in a force balance. So here perpendicular means perpendicular to the ambient magnetic field. So the gradient, perpendicular gradient of their pressure is their current crossed with the magnetic field. The Lorentz force, the pressure gradient. What is the cosmic ray current? We don't actually have to know it. The Lorentz force on the thermal gas is the current in the gas crossed with the magnetic field. Again, we don't have to know that because the gas current is the total current minus the cosmic ray current, and the total current is just the curl of the magnetic field by Ampere's law, and we can now substitute in the pressure gradient. So the cosmic ray pressure gradient perpendicular to the magnetic field lines actually appears in the force equation for the gas, and it kind of crept in through the Lorentz force. We have to understand the parallel dynamics in a different way that really does force us down to kinetic scales. So here I've sketched a magnetic field line in red that has large scale curvature and tiny scale wiggles. And this black helix is the orbit of a particle, a cosmic ray particle. And by and large, this orbit follows the field line and kind of doesn't see these small scale fluctuations. They kind of average out. But there's a special condition, which is that, so if we imagine this being a wave with some frequency omega, wave number k, v is the cosmic ray velocity, and mu is the cosine of its pitch angle. If the Doppler shifted frequency of the wave is equal to a gyro frequency, so the particle goes one wavelength per gyro period, then it's kind of like a resonantly driven harmonic oscillator, and it will strongly respond. So we think that this gyro resonant scattering is the main source of that need-free path for cosmic rays. And we can estimate the diffusion coefficient if we say that, so we have some fluctuation with amplitude delta B. And so the mean field plus the fluctuating field makes an angle, delta theta, of order delta B over B. And a gyro resonant, and the frequency of scattering is the mean squared delta theta divided by delta T. And the scattering is nearly elastic because these waves turn out to be very slow. And so that if we replace delta T by 1 over the cyclotron frequency and delta theta by delta B over B, then we can get a scattering frequency that's proportional to the square of the wave amplitude, and we can translate that into a spatial diffusion coefficient. Now, the theories diverge at this point over what the source of waves actually is. So according to the self-confinement theory, cosmic rays actually make their own waves through this instability, which I'm about to describe. But an alternative is that the waves are just there. They're just part of a turbulent cascade. And we can think of that as confinement by extrinsic turbulence. The propagation model and the interaction model that comes out of self-confinement is a sort of a classical theory of cosmic ray hydrodynamics. I once had to explain what this was to Fox News, who thought it was all a big scam. And confinement by extrinsic turbulence leads to a sort of generalized cosmic ray hydrodynamics. And you can bridge these two theories, and I showed how to do that in a review paper a few years ago. Okay, so how does the streaming instability actually work? Well, I've written down the growth rate for a reason. First of all, this is the resonance condition. So it says that the growth rate, that growth or damping, is driven by gyro-resonant particles. And since the number of F is the distribution function, and since the number of cosmic rays per momentum decreases with increasing momentum, as we saw from that power law, this term tends to damp any wave. But if there's any anisotropy, that can excite the wave. And the anisotropy factor is multiplied by what turns out to be kind of a big number. So V is like the speed of light, it's the cosmic ray particle, And k over omega is the speed of the wave, which turns out to be the alphane or magnetic speed. And in the interstellar medium, it's usually tens of kilometers a second. And fortunately, there's a simplified expression for this, which is here. So the growth rate is some constant that depends on the spectrum times the proton cyclotron frequency, which is a very fast number or large number on astrophysical scales, and it's multiplied by a very small number, the number density of cosmic rays over the number density of thermal ions, which is about 10 to the minus 9 or 10 to the minus 10, and then multiplied by this anisotropy factor, which says that if cosmic rays are drifting at greater than the alphane speed, or alternatively, if they're streaming faster than the wave in the frame of the wave, waves will be excited. And this combination of a very small factor times a very large frequency means that the waves grow in about a year. So they respond very fast to local conditions. So these waves now react back on the cosmic rays, and we can derive a so-called Fokker-Planck equation that describes that. And miraculously, if we look at the wave fields, electric and magnetic fields, and how they act on the perturbation to the distribution function that they cause themselves, this turns out to have the form of a diffusion tensor in momentum space. And the leading term in this is the scattering term. And it's this, which we kind of derived from geometric arguments. And that's the sort of rigorous basis for that scattering theory. We can also take the Fokker-Planck equation and multiply it by particle energy, integrate over momentum space, and get an overall energy equation for the cosmic rays. And that says that the time rate of change of energy density plus the divergence of the energy flux is equal to this not very useful looking quantity, which is the product of the energy in the waves times the rate at which the waves are excited. So it's not very useful looking because we can evaluate this, but we don't really know this. But if we make the assumption, which is justified by the observations, that cosmic rays are almost isotropic and have a short scattering mean-free path, we can derive a relationship between the diffusion rate and the cosmic ray gradient. And if we put that into the energy transfer integral, we get this very simple looking expression, which says that the change in cosmic ray energy, other than divergence of energy flux, is this thing that looks here like frictional heating. So as cosmic rays stream down their pressure gradient relative to the gas, they heat it at this rate. To go a little further under the hood, what's going on here is that the cosmic rays are exciting the waves, and in a steady state, the waves are being damped by the thermal background. And the main damping mechanisms that have been considered historically are friction between ions and neutrals, which tends to damp the waves. This is important in cool gas. There are mechanisms for nonlinear energy transfer to the thermal ions. There's distortion of the alphane waves due to wandering of the background magnetic field. And we can put them all together and come up with an equilibrium streaming rate, wave amplitude, wave dissipation rate, and an expression for the diffusion rate. And whatever mechanism you consider here, it always seems that self-confinement works below a couple hundred GeV in the Milky Way. But we constantly have to watch for new damping mechanisms. They're constantly being discovered. Here are just a few recent discoveries. And we always have to keep going back and asking whether these damping mechanisms are so strong that they wipe out self-confinement of cosmic rays. So far the answer seems to be no. Okay, so now we have this fluid treatment. It was originally developed in the 1980s by Heinz Ferck and his collaborators. They were interested in how cosmic rays interact with shocks. They stream down their pressure gradient at the Alfvén speed relative to the thermal gas. They transfer momentum through their pressure gradient. They heat the gas, and they diffuse with a diffusivity given by this, which can be calculated for marginal stability. So numerical implementation methods have been worked out by Pratik Sharma, by Yanfei Zhang and Peng O, and by Thomas and Frommer. And I believe there's an implementation similar to the Zhang and O implementation in the FIRE collaboration. And this hydrodynamic picture of cosmic rays has been applied pretty much all over the place, to shocks, to heating, the interstellar medium, the intracluster medium, to Parker instability, thermal instability, galactic winds, and galaxy formation. And no one's really done more to pursue this treatment for galaxies than work done here or there at Caltech by Phil Hopkins and his FIRE collaboration. But I always feel funny about showing results done at the institution I'm speaking at, so I'll talk about our own work. So what I'm now going to show you is the various ways in which these transport models matter, why it's important to get it right. So here's some work I did with Mateusz Rostkowski and Karen Yang a few years ago. And we set up a gaseous disk with a halo, and had some sort of standard criteria for how stars form and how much star formation gives you so and so many supernovae, and what fraction of supernova energy goes into cosmic rays. And here on the left, we assume that the cosmic rays are just kind of frozen to the gas, that their diffusion coefficient is very small, and that they don't stream. And what you get is this kind of puffed up disk, which made me wonder if it could be stable. And that sort of led to some work on the Parker instability that I'm not going to describe. But if we allow the cosmic rays to stream at the Alfvén speed relative to the gas, we get this big wind, boom, it just blows up. So is this model more accurate, or is this model more accurate? And it's not only pictures that has an effect on the star formation rate. So here's a comparison of different transport models. So we introduced this kind of fudge factor, the drift velocity divided by the Alfvén speed. Blue here is the model that you saw on the left with no wind and the puffed up disk. You get a big suppression of star formation, although you don't get a wind. And then with green, you get Alfvénic streaming. The star formation doesn't subside quite as much. 4 times the Alfvén speed, 8 times the Alfvén speed. And it has a big effect on the star formation rate and the amount of mass that can be driven out of the wind. So I actually learned something from this study, which is that feedback and winds are not the same thing. So you can have a bigger wind and more star formation. There's not a trade-off between the two of them. In retrospect, it's not hard to understand. Now, if you account for the fact that stars form in dense gas, which is weakly ionized, the waves that scatter the cosmic rays are damped, whether due to extrinsic turbulence or due to self-confinement, there should be some sort of decoupling. And with Ryan Farber, a grad student at Michigan, we investigated what the properties of winds and star formation would be like if we assumed that the cold gas has a larger cosmic ray diffusion coefficient. And it makes quite a difference. You can see that. So in this model, the cosmic rays are frozen to the gas. Here, they just diffuse at the same rate everywhere. And here, they diffuse at a higher rate in the cold gas. And you can see there's a much bigger star formation rate in the case where they're decoupled. So again, is this right? So one possible test of galactic winds driven by star formation or star forming galaxies with cosmic rays is whether the gamma ray luminosity comes out right. So we make these assumptions about the cosmic ray population and how it interacts and try to predict what the gamma ray luminosity should be. So here on the left is a model of the Large Magellanic Cloud that Chad Bustard made, trying to put in the star formation rate in the LMC over the past gigayear as reconstructed by Harris and Zaritsky. So here is the observed flux of gamma rays. Here's the calorimetric limit, and these black dots are our model. Obviously, does not work well. Here's some work by TK Chan et al. Based on the fire simulations. Different transport models compared with data. Again, too many gamma rays in the models. And then a really exhaustive study led by Phil Hopkins, many different transport models. The model that works best, the model that's not in, that doesn't strongly disagree with the
Ellen, this is Shri.
Say what? Hi, Shri.
Hi. When you say gamma ray, are you talking of collision of cosmic rays with ambient?
Yes, I'm talking about primarily the pionic gamma rays.
Okay, so you're making some assumptions of the penetration of certain kinds of your 3 GeV. No, it'll be, yeah.
Well, they're right. So they are above, well, they're certainly above the threshold.
Yeah, sure. But you're assuming that your typical 3 GeV proton penetrates every molecular cloud.
Well, I'll get back to that. So I'm going to present some recent work that Chad and I did, which tries to really look at this. We are making an assumption, and perhaps this is what you're asking. We are assuming that the transport of the higher energy cosmic rays, say at 100 GeV or so, is sort of similar to what it is in the Milky Way. I mean, you could say, well, the 3 GeV cosmic rays are described by these transport models, but there's just a completely different transport model for the higher energy cosmic rays. And if you go to a high enough energy, that's certainly true. But I think that this discrepancy does have to be taken seriously, and I think it should be taken I think that we should really pursue the consequences of the model as carefully as possible, and then see if there just has to be something else. Does this address your question at all?
Well, it addresses my concern, but let's, I'll wait till you get to the,
okay.
that distinction.
Yeah, good, okay. Okay, so if we take this discrepancy seriously, then we have to come up with a physics-based model for how cosmic rays interact that either predicts a very large boost in the streaming speed or has a much larger diffusivity than what we infer in the Milky Way and what we calculate from any of these models. Okay, so now I'm going to come back to this, but it's going to look at first like a deviation. I'm going to talk about bottlenecks and pressure anisotropy instability. So it was understood really by one of the pioneers in the field, John Skilling, back in the early 1970s, that the streaming instability predicts a kind of inherently intermittent model of cosmic ray confinement. And that's because if you have perfect coupling and you treat the cosmic rays as having a relativistic equation of state, there's this conserved quantity. The square of the cosmic ray pressure divided by the gas density to the 4/3 is constant along magnetic field lines. So suppose the cosmic rays are streaming along down their pressure gradient at the alphane speed, and they go to a place where the gas density starts to increase. So if the gas density increases, then the cosmic ray pressure must also increase. But we saw that in the framework of frequent scattering theory, the streaming and the pressure gradient should be related. And this kind of makes physical sense. Things tend to flow down their pressure gradient. So now we have the cosmic rays streaming down their pressure gradient, except that their pressure gradient seems to be, their pressure seems to be going up. So what happens? So what Skilling said, he said, well, this is just an irreconcilable paradox. What'll happen is that the cosmic ray pressure will go flat. They'll stream along at the sub-alphanic alphane speed, the minimum alphane speed that you have where the density of the gas is very high, and you just won't have any cosmic ray coupling to the gas. And this was not actually shown until a few years ago, and I'll describe that. But to motivate this question a little bit more, if it needs it, here's an image of the coma cluster in X-rays, and I've sketched in a rather tangled magnetic field, which we think the coma cluster has. The radio polarization is fairly low. And so these magnetic field lines are constantly dipping in and out of denser gas. And how will cosmic rays stream along field lines like these? What does it mean to stream down their density gradient, their pressure gradient, when the field lines are just wandering through high and low pressure regions? So we looked at a much simpler problem beginning in 2017 with Josh Wiener. So we have a cosmic ray source. We have an initially straight magnetic field. We have a cloud here. We assume everything is perfectly ionized. And what happens? Well, if there's no cloud, then you turn on the cosmic ray source and a front kind of moves along. And it eventually, so by 6 mega years, which happens to be about an alphane transit time across the system, this supposed invariant quantity really does look pretty constant. But now we put a cloud in. So we put in a very simple cloud in one dimension with this density distribution and a consequent dip in the alphane speed. And the cosmic ray pressure really does go flat. It's not just flat to the eye. I'll show you later on that it is really, really flat. So in this region here, as Skilling predicted, there are no waves, there is no coupling. Then when the cosmic rays get to past the density maximum, they re-engage. They can actually accelerate the cloud. This is a combination of the acoustic pulse that they drive in front of them if the sound speed is high enough. This heating in the front can kind of erode the cloud. And so over time, the cloud moves its center of mass, but it also shrinks. And if we assume that there's effective radiative cooling, then the cloud just starts to go. And these ripples here are not just some kind of numerical noise, they're actually sound waves that bounce back and forth within the cloud. So this bottleneck, this pressure bottleneck that can form behind clouds, between clouds and the source, can actually drive the cloud, which made us wonder if you could actually drive cosmic ray, you could actually drive multi-phase galactic winds with cosmic rays in some way. And we resolved this front on the far side of the cloud. You can see that the cloud has a very large interior cosmic ray pressure, makes a transition from cool to hot. So there's this trade-off here between the gas pressure and the cosmic ray pressure. And we actually computed some line strengths and compared them to what was observed in some halo clouds by Bart Wacker. And, it does actually better than most of the other models. It seems like a competitive model. So Chad looked at this again, taking into account some different effects. So we considered a partially ionized cloud. We went to higher dimensions, as I'll show you. And we also looked at the effect of resolution. And what we found actually is that resolving this interface between the cloud and the intercloud medium is quite important. Here's a comparison between two different times, the same time. So we turn on a burst of cosmic rays that lasts for about 30 mega years. In both cases, we get a bottleneck. We get a much more extreme effect when we have 1/4 parsec resolution than we have at 2 parsecs resolution. It seems like you need about 10 cells in this interface to get the full pressure drop right. And you also get this funny little thumb, this little feature here in the cloud density that's due to heating. You get a lot of heating here where the cosmic ray pressure gradient is very large. So this is a bit worrisome in the context of global simulations. In 2 dimensions, so what I showed you there was in 1 dimension. In 2 dimensions, the magnetic field strength plays a big role in what we see. So here's a fairly strong field, and the field lines manage to stay straight despite the buildup of cosmic ray pressure behind. But if we consider a weaker field, then we get all this warping. So we still get a bottleneck. We still get a region of higher cosmic ray pressure and lower cosmic ray pressure here. This cloud gets compressed, and the field lines get sort of dragged out into these lobes. And this situation, and actually this one too, are both ripe for pressure anisotropy instability, which I'll describe. Here's cloud acceleration. It's not very dramatic, but you can see the effect of field strength on the terminal velocity of the cloud. It's probably capped at the alphane speed. This is a fully ionized cloud. This is a weakly ionized cloud. In a weakly ionized cloud, the alphane speed essentially goes up, even though the total mass density goes up. The ion density goes down, which raises the alphane speed. You still get some momentum boost, but it's smaller. Then we looked at whether you would get bottlenecks in a clumpy medium. And so here's a collection of clumps, and you can see the cosmic rays. So this kind of revisits the question of, do cosmic rays squirt out through the holes in the density? And you can kind of see them working their way around the clouds. So the white contours are higher density, the yellow, the red, progressively higher density, and the cosmic rays kind of snake their way around. Still get momentum transfer. These are, you can see that the greatest momentum transfer comes with the weaker magnetic field. These are just parameters of the clump size and the clump amplitude. So what are the implications for gamma ray emission? We did this very careful study. We have low density gas, high density gas, high resolution simulations, different field strength. And here is a plot that summarizes everything. So here is a plane of collisionless loss. So this is the VA.grad P cosmic ray term. And this is the collisional energy loss. We took that into account, a simple model of gamma ray production, pion production. And you can see that the models, which have different, different clump properties, some of them have diffusion, some of them just have streaming. Here's one in 3D. Different ionization fractions, fully ionized, weakly ionized. They sit in a fairly small part of parameter space. So it's not clear that the gamma ray emission distinguishes all that well between different transport models. And that also suggests that this overproduction of gamma rays is not going to be cured by the physics that we've put in so far. We need something else. So what could that something else be? Well, so to kind of summarize what we know about these bottlenecks, do they form or not? If they form, then there are these regions of large regions of space where cosmic rays are not coupled to the gas. They heat only the interfaces. They accelerate only the clumps. I said the profile was very flat. Chad measured it. The gradient length scale in the simulations of a single cloud, 1 kiloparsec away from the boundary, this is how flat it is. The gradient length scale, P over grad P, is about 100 megaparsecs. If the cosmic rays are coupled, no bottlenecks, then they heat the gas everywhere and they impart momentum volumetrically. So let's go back and look more carefully at this bottleneck question. Okay, so up until now, we've considered only drift anisotropy, but there's also pressure anisotropy. The perpendicular and parallel pressures of cosmic rays can be different, and I'll describe in a couple of minutes what could make them so. So for drift anisotropy, which is what's classically considered, the waves that go in the same direction as the drift are the unstable ones, and both circular polarizations of waves, so left and right circularly polarized waves, they can both be unstable. The wave itself is going in the same direction as the drift, but the waves of different circular polarizations scatter cosmic rays going in different directions. In pressure anisotropy, waves going in both directions are unstable, but in each direction, there's only one sense of circular polarization that is unstable. So this instability was first discussed some time ago by Alex Lazarian and Andrei Berezniak, and I wrote a paper about it last year. The growth rate of the pressure anisotropy instability is actually very similar to that for the drift anisotropy. Pressure anisotropy, namely a difference between the parallel and perpendicular pressures that's only of order the Alfvén speed divided by the speed of light, can be unstable. And the growth rate is similar to the streaming instability growth rate. So cosmic rays in a situation like this bottleneck situation can drive their own pressure anisotropy. And remember that VA over C is about 10 to the minus 4. So even if the field lines look completely straight to you, they can be bent enough to be unstable. So the field gets warped by the buildup of cosmic ray pressure and the acoustic forerunner behind these clumps. And as the field lines warp, because they warp slowly compared to the gyro period of a cosmic ray, there are two kind of conserved quantities about the particle motion. One is the magnetic moment of the particles, essentially the magnetic flux through the orbit. And the other is a longitudinal action. And so the parallel and perpendicular pressures, parallel and perpendicular momenta evolve in different ways in a warped magnetic field. The sort of best known example, which you may know, is the tendency for particles to be repelled from regions where the magnetic field gets very strong, so-called magnetic bottles. And that's because as cosmic rays or particles move into a region of stronger magnetic field, their perpendicular momentum has to increase, but if the field is static, their total momentum has to stay the same, and this can eventually drive their parallel momentum down to 0, and then they reflect, and then they're trapped. So this warping of the field creates pressure anisotropy, which will be unstable, and there's some level of scattering which will isotropize the cosmic rays enough to keep them marginal. So let's see if we can figure out what that is. So we go back to the Fokker-Planck equation, which I've written again. This was what we kept before, the gradient term. Now we're going to zero it out. The evolution term is always kind of slow. This represents this magnetic mirror force, and this is the divergence of the unit vector pointing along the magnetic field, and it can be written like this. So it actually is proportional to the gradient of the magnetic field. And here is this scattering term. So now we're going to balance the scattering term with the warping term instead of with the gradient term. And here's what we get. We can actually solve for the scattering rate. And it turns out to be of order the speed of light divided by the scale, the length scale on which the magnetic field is varying. And that leads to a mean free path, which is about the same as the magnetic length scale. So that is all the scattering that you need to keep the pressure anisotropy marginally stable. And this is big. This isn't for the bottleneck problem that I showed you, the magnetic length scale is maybe 100 parsecs, maybe tens of parsecs, but more like 100 parsecs. So the mean free path is longer, the scattering rate is lower, and so this is more diffusive. This is a more diffusive system than what we get from the streaming instability. On the other hand, the streaming instability alone predicts that there should be no scattering whatsoever. So we get this very weak coupling in the regions where the classical prediction is that bottlenecks should form. And I don't really see any way out of this. So the sort of bottleneck prediction is that the waves go away, the cosmic rays their pressure is building up in this, so they're bloating up the magnetic field, they're warping the field, that is making them unstable to pressure anisotropy instability. So something must happen. If we account for pressure anisotropy instability, the totally decoupled bottleneck cannot survive. So what I'd like to propose is that self-confinement works, self-confinement by the streaming instability works when cosmic rays are streaming down their pressure gradient, and the pressure gradient and the density gradient are aligned, both going down, both going up. But when they're anti-aligned, there's pressure anisotropy instability. And the pressure anisotropy instability does couple the cosmic rays to the thermal gas, but it's weaker. And it gives you a very diffusive system, which may be what's required to reduce the gamma ray flux. So remember, this was one of the alternatives. This was one set of models that work better, models with a big diffusion coefficient. So this is my sort of meta summary. Cosmic rays are important for feedback. I hope if nothing else I've convinced you of that. And they're important because they cool more slowly than the thermal gas, which provides a sort of sustained pressure push. If bottlenecks form, they might drive multiphase winds even, but this excess gamma ray luminosity prediction really has to be addressed and solved. And maybe this highly diffusive transport that is triggered by bottlenecks that I've just described, maybe this could be the missing ingredient. So that is what I have to say. Thank you.
Okay, thank you, Ellen. So we have time for a few questions here. Are there any questions from the audience? So Ellen, I have what might be a very naive question. So I'm sure you know about the Fermi bubbles, and which are now X-ray bubbles as well, I think, with Eurocity. Yeah. I was wondering if cosmic rays are relevant to blowing out those bubbles or producing the X-ray or gamma ray emission that we see there.
Yeah. So as you probably know, there are a couple of theories for the origin of the Fermi bubbles. One of them is that they're due to star formation. So you have this, high star formation rate in the molecular ring, and so star formation feedback, which could include cosmic rays, would be part of what energizes the Fermi bubbles. The other theory is that they were created by a burst of AGN activity a couple of million years ago in our galaxy, and it's actually that theory that I've been associated with. Karen Yang and Mateusz Rostkowski have really led that work, and we found that so this actually, we have a leptonic model for the gamma rays, where the bubbles are inflated by AGN jets. What's sort of appealing about that is that we see AGN jet inflated bubbles in galaxy clusters on much, much larger scales. And this could be sort of a laboratory for studying. But what I've described here would be more relevant to the star formation scenario. Does that address your
But
question?
regardless of what the source of power is, are the cosmic rays relevant for blowing out and shaping the features that we see on kiloparsec scales?
Right. Well, so what I've described is mostly a hadronic model, and I don't know, if it's star formation driven. I don't know if you can really, if the kind of normal cosmic ray population that I've described is, I have not completely thought that through. So I don't think your question is naive.
Oh, okay, thanks. So we have a question from Phil.
Thank you. Thank you, Ellen, for the talk. I just had hopefully a quick question. The pressure anisotropy instability, maybe you said this, but you went by a little quick. How big an anisotropy in the pitch angle distribution does that imply, or am I just misinterpreting it? And is that a potential issue with, do you have to only have that anisotropy occur in these weird regions, and then it sort of reverts to a close to isotropic distribution to explain the sort of local ISM observations, or is there tension there? I'm just curious.
So the instability, pressure anisotropy instability, is triggered by a tiny pressure anisotropy of order the Alfvén speed divided by the speed of light. So I don't think it really affects the dynamics. If you want to describe the force on the gas, grad P cosmic ray is good enough. A correction of order 10 to the minus 4 is not really going to make any difference. And I think that so normally, if we go back to, so this term is like the speed of light times the cosmic ray distribution function divided by their length scale. And this term is involves the magnetic length scale, which under, sort of normal conditions wouldn't be that different from the cosmic ray length scale, but it has the cosmic ray anisotropy in it, which we know due to one instability or another is going to be tiny. So under normal conditions, the gradient term is much, much bigger than the anisotropy term. It's only in situations like bottlenecks that we're sort of forced into considering this anisotropy term. And as long as the waves can grow at all, I think that the anisotropy will be small enough that you don't have to work with the tensor form of the pressure in calculating the effect on the gas dynamics. Does this answer your question?
Yes, very much. Thank you. Yeah.
Okay, so now we have a lot of questions. I don't think I'm going to be able to get to everybody here, but I want to give a chance for Catherine to ask a question. So Catherine, go ahead.
What are the size scales of the bottlenecks?
Good question. So here's what we've put in. So basically, what we've created here, this clumpy medium, is a medium with a sort of, it's all kind of within a kiloparsec. And so these bottlenecks are tens of parsecs or 100 parsecs or so. So there's kind of a practical range of bottleneck sizes. If the clumps were very close together, say closer than a mean free path, you couldn't really use a hydrodynamic theory of cosmic rays. I'm not really sure what would happen then. And if the density maximum were so far from the source that the alphane travel time were longer than sort of characteristic dynamical time, conditions would just keep changing. And so you wouldn't really ever form a steady state bottleneck. So I think that bottlenecks are most important when you have density structures where the alphane travel time between the structures is reasonably short compared to the sort of global evolution of the system. Does that make sense?
Thank you.
Okay, we're about out of time. I'd like to get one last question from Cameron, and that will be the last one.
Great, thanks. Excellent talk, Ellen. I just had a quick question, and it's a bit related to Catherine's previous question, and that is, you talked about in some of the models that you and Chad did, where you had the cosmic rays flowing into an overdense region and the impact that resolution played on things. And you said that when you went to higher resolution, you got slightly different behavior with the pull off of that little structure. Did you find convergent behavior, and what appears to be so this is between a quarter parsec and 2 parsecs resolution. Did you find basically convergence at sub parsec or?
Yeah, we did. And so you could say, well, why 2 parsecs, why quarter parsec? It's, so we set up a cloud, with actually it's a hyperbolic tangent profile, and whatever width we put in for that cloud, we need about 10 cells within the layer to get convergent behavior.
I see. Okay, it's interesting that you end up with this kind of sub-parsec scale, since that's so relevant for the size of the predicted size of cold clumps in the CGM, or that sort of thing predicted by a bunch of other studies too. So it's cool that this is all aligning on similar scales.
Yeah, I know this has become active, and I'm going to be participating in this KITP, virtual CGM.
Yeah.
Unfortunately, just virtual. So I'm hoping that we get in some good discussions of that. Are you going to be at that too?
Yeah, I'm the primary.
Oh, that's right. You're one of the people. Okay. Well, thank you for putting it on. You're very brave.
Okay, I'd actually like to do one more question from George Halou. George, do you still have a question?
Yes, and this relates to the scale of these bottlenecks. What is the assumptions you're making for the scaling between the magnetic field strength inside these clouds and the density of the clouds, and does that really affect the results at all?
Right. So we start with a completely uniform situation. Start with a straight magnetic field, just put in a cloud, a denser cloud in pressure equilibrium with its surroundings. And then, we let the system evolve. Now, my impression is that in the interstellar medium, there's really not much of a field strength density relation until you get to molecular clouds. So a cloud, of density 100 is not necessarily going to have a stronger field than a cloud of density 20, but it will be stronger, again, in a molecular cloud. And we really have not considered extreme molecular cloud conditions, with an ionization fraction of 10 to the minus 7 or 10 to the minus 8. But that is a good question, sort of the whole role of magnetic structure. And actually, one of the things that I've wondered apropos this gamma ray luminosity problem is whether it's telling us that magnetic flux is just not the magnetic flux through the clouds is just not as high as we think it is, that clouds are maybe even topologically somewhat disconnected from the galactic field, and that's keeping the cosmic rays out. I really don't know. It's a good question.
All right, thanks.
Okay, well, we're a bit over time now, so I think we'll wrap it up there. Thank you, Ellen, for